This is Bob Capetta from the University of Illinois at Chicago, and this is the virtual lecture for January 30th, 2019. So here's the first review question I want you to look at. Construct an equation for the function that defines the following graph. Notice we have a vertical asymptote here of one type. We have a vertical asymptote here of another type. X-intercept at 2, 0. And y-intercept at 0, 4. So my advice is to pause the video, try it yourself, and when you're finished, check your results by advancing the video. And so hopefully you have an answer. Looking at this, we're going to first focus on our vertical asymptotes. I have one at x equals -1, so I will need to have x plus 1 in the denominator. I also have a vertical asymptote at x equals 3, so I'll need x minus 3 in the denominator. But notice they're of different types. X equals -1 going up on both sides. That tells us that this asymptote will have an exponent of 2, so we'll need x plus 1 squared downstairs. Here at x equals 3, they're going opposite directions, down to the left, up to the right, so I will need x minus 3 to the first in the denominator. So this is what we're dealing with. Now, we also have an x-intercept at 2, 0. So if that's the case, I'm going to need x minus 2 in the numerator. Notice, if we have x minus 2 in the numerator, plugging 2 in, 2 minus 2 gives me 0. If the x value is 2, the y value is 0. But I also need to solve for a multiplier, which I'm going to call a. So how do we solve for a? We're going to use the y-intercept. We have 0, 4 here. F of 0 is 4. So 4 is f of 0. Plugging in 0, a times 0 minus 2. 0 plus 1 squared is 0 minus 3. 0 minus 2, -2 times a upstairs. 0 plus 1, 1 squared is 1. 0 minus 3 downstairs, minus 3 downstairs. -2 over -3 becomes 2/3. So plugging 0 into this function, we get 2a over 3, but our y-intercept was 0, 4, so f of 0 is 4. Tells me 2a over 3 is 4. To solve for a, multiply both sides by the reciprocal, multiply both sides by 3/2. And what is 4 times 3/2? 12 divided by 2 is 6. So a is 6. Plugging 6 in for a in this function will give us our final answer, that f of x is 6 times x minus 2 over x plus 1 squared times x minus 3. So as a quick review of how we construct graphs for rational functions. Let's take a look at our next review question. We have a function f of x is 3x plus 1, and a function g of x is 2x squared plus 5x minus 7. We want to evaluate the following. So we have f circle g of -1, which means f of g of -1. F circle g of x, which means f of g of x. G circle f of x, which means g of f of x. So again, I'm going to ask you to pause the video, work those three out on your own, and then check to see if you've done it right by advancing the video. So I assume you have your answer, so I will continue. So there's our two functions. F of x is 3x plus 1, and g of x is 2x squared plus 5x minus 7. We want f circle g of -1, which is f of g of -1. So the first thing I need to do is I need to plug -1 in for g. So plug -1 into x for the g function to find g of -1. So I'll need 2 times -1 squared plus 5 times -1 minus 7. 2 times -1 squared plus 5 times -1 minus 7 to give me g of -1. -1 squared, of course, is -1 times -1, or positive 1. 5 times -1 is -5, minus 7. 2 minus 5, -3, minus 7 is -10. So g of -1 is -10. We'll plug -10 in where we have g of -1. Now I have f of -10, but what does f do? 3 times the input plus 1. So the input is -10. I need 3 times negative 10 plus 1. 3 times negative 10 is negative 30. Negative 30 plus 1 gives me an answer of negative 29. So f circle g of negative 1, which is f of g of negative 1, gives us an answer of negative 29. Our next question, again looking at f of x and g of x, is to evaluate f circle g of x, which means f of g of x. So I've got to plug g of x into the function f. What does the function f do? 3 times the input plus 1. So plugging 2x squared plus 5x minus 7 into the function f. Again, 3 times the input. F of x is 3x plus 1. So f of something is 3 times something plus 1. But the something that I have here is 2x squared plus 5x minus 7. That will be inputted into the brackets. So it'll be 3 times 2x squared plus 5x minus 7 plus 1. Distributing here, 3 times 2x squared is 6x squared. 3 times 5x is 15x. 3 times negative 7, negative 21. So 6x squared plus 15x minus 21, add 1, minus 21 plus 1, of course, is minus 20. And that will give us f circle g of x, or f of g of x. Our next example is to look at g circle f of x. Generally speaking, composition of functions is not commutative. You would not expect f circle g and g circle f to be the same. So we just did f circle g of x. Let's take a look at g circle f of x. G of f of x. We're going to plug f of x, 3x plus 1, into the function g. Sorry about that. I think I need to turn off my autosave. So I get g of 3x plus 1. G of f of x is g of 3x plus 1. Now what does g do? 2 times the input squared plus 5 times the input minus 7. So it's 2 times something squared plus 5 times something minus 7. That is our definition of the function g. What are we plugging in? 3x plus 1, 3x plus 1. So we'll get 2 times 3x plus 1 squared plus 5 times 3x plus 1 minus 7. Now be careful with 3x plus 1 squared. That's 3x plus 1 times 3x plus 1. 9x squared plus 6x plus 1. Don't ignore those middle terms. So multiplying that out, again, 3x plus 1 quantity squared, 9x squared plus 6x plus 1 plus 5 times 3x is 15x, 5 times 1 is 5, minus 7. Distributing here, 2 times 9x squared is 18x squared, 2 times 6 is 12x, 2 times 1 is 2. And then looking for like terms, I see 12x plus 15x would be 27x. And interestingly enough, 2 plus 5 is 7, minus 7 is 0. So my answer here is going to be 18x squared plus 17x. Okay, here I have a more challenging question. We've got 2 rational functions defined here. F of x is 2x over x minus 3, and g of x is 1 over x plus 2. I'd like you to evaluate the domain of f and the domain of g, maybe express those in interval notation. Find f circle g of 5, which of course means f of g of 5. Find f circle g of x, which means f of g of x, and then to conclude this, evaluate the domain of f circle g. So I'm going to ask you to try these problems. Pause the video, and when you're finished, watch to see how I solve the problems. Okay, let's take a look. Domain of f, x cannot be 3. We have to throw out 3. You cannot divide by 0. So the domain of f is all real numbers except 3. Write at an interval notation, negative infinity to 3, not including 3, union 3 to infinity. And as far as g goes, we can't be negative 2. So the domain of g tells us x cannot be negative 2, so let's throw that out. The interval from negative infinity to negative 2, union from negative 2 to infinity. What's next for us? We want to find f circle g of 5. F of g of 5. So the first thing we need is g of 5. We'll plug 5 into the g function. Plug 5 in for x. 5 plus 2 is 7. G of 5 will be 1/7. And then we'll replace g of 5 with 1/7. So this becomes f of 1/7. Now what does f do? 2 times the input over the input minus 3. 2 times the input over the input minus 3. What is the input? Here the input is 1/7. Now 2 times 1/7 upstairs is 2/7. Downstairs, 1/7 minus 3. Well, 3 is 21/7, so 1/7 take away 21/7 would give me negative 27. And then to divide these fractions, 2/7 divided by negative 27 is the same as 2/7 times 7 over negative 20, or 2 over negative 20, which reduces to negative 1/10. So f of g of 5 is negative 1/10, but a little tricky arithmetic there for you to work with, so make sure you're clear on that idea. What shall we do next? We're going to look at f circle g of x, which is f of g of x. So this time I'm going to place 1 over x plus 2 into my f function. But what does f do? 2 times the input over x minus 3. So it'll be 2 times g of x over g of x minus 3. Notice there's your g of x. 2 times 1 over x plus 2. 2 times the input over the input 1 over x plus 2 minus 3. Now this algebra gets tricky. In the last example, the arithmetic got tricky. First thing I'm going to do is 2 over 1 times 1 over x plus 2. This numerator is going to be 2 over x plus 2. Now to simplify this fraction, we're going to multiply top and bottom by x plus 2 to clear the denominators. Multiply the top by x plus 2, all that's going to be left is 2. Multiply the bottom by x plus 2, let's talk about that one. So there you go. Top multiplied by x plus 2, bottom multiplied by x plus 2. X plus 2 over 1, x plus 2's cancel, the top is just 2. But on the bottom we have to distribute. X plus 2 times 1 over x plus 2 is just 1. X plus 2 times 3 is 3 times x plus 2. So notice by doing that, all of the fractions are gone. Multiplying top and bottom by the common denominator eliminates all of the fractions. So that's very nice. Now I still need to simplify the denominator. Negative 3 times x is negative 3x. Negative 3 times 2 is negative 6. And 1 minus negative 6, of course, is negative 5. So we have 2 over negative 5 minus 3x. And remember, the denominator cannot be 0. We cannot do division by 0, so in terms of our domain, we need to keep that in mind. So here's our functions that we started with. There's f of x and there's g of x. F circle g was this, and our question is, what is the domain of f circle g? Now you may think all you've got to do is throw out the value when this is 0. Well, let's find that. Negative 5 minus 3x cannot be 0. Adding 5 to both sides. Negative 3x cannot be 5. X cannot be negative 5/3. So you may think that's the only thing we have to throw out to get the domain of f circle g, but not quite right. Remember, we have to do g of x first. Negative 2 is not in the domain of g. We said that earlier. If you plug negative 2 into this, you have g of negative 2, you have 1 over 0. That is not acceptable. That cannot go any farther. What I say is that destroys the function. So negative 2 is not in the domain of g of x. You cannot go further to evaluate f because you don't have a value for g of negative 2. So negative 2 must be thrown out as well. So we throw out negative 5/3, we throw out negative 2. Everything else is okay though. So we construct our interval notation answer. Negative 2 is a little bit less left of negative 5/3, a little bit less than negative 5/3. So negative infinity to negative 2. Then negative 2 to negative 5/3. Remove negative 5/3, negative 5/3 to plus infinity. So that's how we would define the domain of f circle g in interval notation using that approach. Okay, I have another set of problems for you to work on. F of x is 3x plus 1. Determine f inverse of x. Next one, g of x is x squared minus 3. Explain why this function does not have an inverse. We're going to make a small change to it. We're going to let h of x equal x squared minus 3 for x greater than or equal to 0. Now you can determine h inverse of x. And the last example here, k of x is 2x plus 1 over x minus 5. Determine k inverse of x. So let me ask you to work on those 3 problems. When you're finished, go ahead and advance the video, but pause it now. Okay, let's take a look. F of x is 3x plus 1. That is what the graph of 3x plus 1 looks like. Notice y-intercept of 1. Slope, it goes up 3, goes over 1. This is a line, an oblique line. If you would switch the x's and y's, which is what we do for inverse functions, it'll be another line. It's not going to violate the vertical line test. But for a function to have an inverse, it has to pass the horizontal line test. No horizontal line can cut this in more than one point. Any horizontal line you see, and you can see the grid lines here, the grid lines only cut it in one point. So it is a one-to-one function. A horizontal line cuts it in at most one point. It is a one-to-one function, so this will have an inverse. Now, how do we find the inverse? I like to use x and y notation. And the inverse just means you switch the x and y. Y becomes x, x becomes y. By doing that, this then becomes x equals 3y plus 1. And then our goal is to solve for y. When we solve for y, we will be left with the inverse function. So subtracting 1 from both sides, we get x minus 1 is 3y. And then divide both sides by 3. X minus 1 over 3 equals y. This is the inverse function. That is f inverse of x. F inverse of x will equal x minus 1 over 3. Now I'd like to graph this function together with this function in red, which is f. So the function in red is 3x plus 1. The function in blue is what I have as f inverse of x. And there's something kind of interesting about this. These are mirror images of each other through the line y equals x. So if you'll notice 0, 0, 1, 1, 2, 2, 3, 3. We have mirror images through that line. That's a way for us to visually identify a function and its inverse. It will be the mirror image through the line y equals x. And of course, the way we would do that, for example, this is the point 1, 4 on the function. You switch x and y. So 4, 1 would be on the function inverse on f inverse. So a nice visual representation of the inverse of the function. Our next example is g of x is x squared minus 3. Now, here's the picture. This does not pass the horizontal line test. Now, why is that a problem? If you would switch the x's and y's, all of a sudden it would be a sideways parabola like this, and that would fail the vertical line test. That is not a function. So g inverse does not exist. There is not a function that is the inverse of this. This fails the horizontal line test. So horizontal lines intersect the graph in 2 points, so the function does not have an inverse. We say the function is not one-to-one. This is not a one-to-one function, so it doesn't have an inverse. But we can modify it a little bit so that we have a new function that does pass the horizontal line test. And that's what we did here by creating h of x, that previous function, but only for values when x is greater than or equal to 0. So now I have a function that does pass the horizontal line test. No horizontal line cuts this in more than one point. So knowing that, we can go ahead and find the inverse. So how do we do that? We use x and y notation, replacing h of x with y. And the whole point of the inverse is to switch x and y. X becomes y, y becomes x. So this equation becomes x equals y squared minus 3. And then we solve for y. Adding 3 to both sides. X plus 3 is y squared. Taking the square root of both sides, y is the square root of x plus 3. Not plus or minus, because if we had plus or minus, we'd again fail the horizontal line test. We are only dealing with positive values of y. If the x values are positive here, if we take the inverse, the y values have to be positive. So no need for negative root x plus 3. So my inverse function, h inverse of x, is the square root of x plus 3. Now we've got this function h in red. I'm going to graph h inverse in a different color, and we'll see what that looks like. H is in red, h inverse is in blue, and they are supposed to be mirror images of each other across the line y equals x. Again, notice this is the point -3, 0. Switch x and y. This is the point 0, -3. And then if I go ahead and draw in the line y equals x, you will indeed see that the red function h and the blue function h inverse are mirror images across the line y equals x. One more function for us to work with here to find the inverse, and the algebra here gets a little challenging. So I have k of x is 2x plus 1 over x minus 5. Just to convince you, we'll take a look at the graph, and indeed that passes the horizontal line test. Yes, this is asymptotic. You notice the horizontal asymptote is y equals 2, but it never actually becomes horizontal. So no horizontal line cuts the graph in more than one point. This function has an inverse. This is a 1-to-1 function. So we know that. We can find the inverse. We're going to use y equals notation and then switch the x and y's and solve for y. So there's our idea. Y equals 2x plus 1 over x minus 5. To find the inverse, x becomes y and y becomes x. So x equals 2y plus 1 over y minus 5. And then we want to solve for y. First thing I have to do is multiply both sides by y minus 5. That will clear the denominator on the right side. So on the right side, y minus 5 cancels y minus 5, leaving me with 2y plus 1. On the left side, we get xy minus 5x. Now I have to solve for y, so I want to get all the y's on one side, all of the non-y's on the other. So let's get all of the y's on the left side. Subtract 2y from both sides, and then add 5x to both sides. If I subtract 2y from both sides, I'll get xy minus 2y on the left side. If I add 5x to both sides, I'll get 5x plus 1 on the right side. Now I want to solve for y, so factor out the y. If I factor out the y here, I get y times x minus 2 equals 5x plus 1. And then to solve for y, I will divide both sides by x minus 2. So we get y equals 5x plus 1 over x minus 2. And that is my formula for k inverse of x. So k inverse of x will be 5x plus 1 over x minus 2. And let's take a quick look at the graphs of those. So k of x will be there as well as k inverse. K of x is in red. What I just defined as k inverse is in blue. And the line y equals x is in green. That serves as the mirror. So these two functions are mirrored images across that line y equals x. And that will conclude the review portion of this lecture.